Just before Silicon Valley, people used to store data in various ways. Hi guys, welcome back to Nerd Talk. I am really excited to have you here. So sit back, relax, and get ready for our 14th journey together. In this video, we will journey through the incredible history of computing, from prehistoric tally marks carved into bones to the birth of modern computers and artificial intelligence. We'll explore ancient mathematics, the invention of zero, algorithms, mechanical calculators, binary code, and the brilliant minds of Charles Babbage, Ada Lovelace, and Alan Turing, who shaped the digital world we live in today. Before Silicon Valley, before electricity, before machines, humans had already begun computing. Every computer on Earth traces its ancestry back to a simple human problem: remembering information. Long before screens and microchips, our ancestors invented ways to store memory outside the human brain. That single idea would eventually lead to calculators, machines, artificial intelligence, and the digital world itself. The first computer was not made of silicon, it was made of bone. Around 43,000 years ago, humans carved marks into bones to count days, animals, food, or lunar cycles. The Lubombo bone, discovered in southern Africa, contains 29 carved notches. Thousands of years later, the Ashango bone revealed even more advanced mathematical patterns. These marks represented something revolutionary: memory stored outside the human mind. Every modern computer still follows this exact same principle. As civilization emerged in Mesopotamia, humans developed one of history's most powerful mathematical systems, base 60. Unlike base 10, the number 60 can be divided evenly in many ways, making calculations easier for trade and astronomy. Using wedge-shaped symbols called cuneiform, Sumerian scribes recorded taxes, grain supplies, and business transactions on clay tablets. Even today, your clock, geometry, navigation, and GPS still depend on Sumerian mathematics. Ancient Egypt transformed mathematics into monumental engineering. The Rhind mathematical papyrus contained dozens of advanced mathematical problems involving geometry, fractions, and construction calculations. Egyptian engineers aligned the Great Pyramid to true north with astonishing accuracy, all without modern tools. Using ropes, shadows, stars, and arithmetic, they demonstrated that mathematics could shape civilization itself. Deep within the rainforests of Central America, the Maya created one of history's most advanced mathematical civilizations. They developed a base 20 system using dots, bars, and one revolutionary symbol: zero. Their astronomers tracked planetary movements and calculated the solar year with incredible precision, using only naked eye observation. Their temples became observatories, and their calendars became predictive computational systems. One of humanity's greatest inventions emerged in ancient India: the decimal place value system. This revolutionary method allowed numbers to change meaning based on position, making calculations dramatically more efficient. In 628 CE, Brahmagupta formalized operations involving zero, transforming mathematics forever. Through trade and scholarship, Indian numerals spread across the world and eventually became the foundation of modern computing. As civilizations grew larger, trade became more complex. Farmers, merchants, and tax collectors needed faster ways to calculate enormous quantities of goods. Human memory alone was no longer enough. And so, humanity created one of the first true calculating devices: the abacus. The earliest abacus systems appeared over 4,000 years ago in Mesopotamia. Some used pebbles sliding across lines drawn in sand, while others used carved wooden boards. It may seem simple today, but this device changed the speed of human calculation forever. As trade routes connected civilizations, the abacus evolved into many forms across the world. In China, the swan pan used multiple beads for complex arithmetic. In Japan, the soroban became faster and more refined. In Russia, the shoti used horizontal wires for rapid calculations. For centuries, merchants and mathematicians could perform multiplication, division, square roots, and commercial accounting entirely by moving beads with astonishing speed. Skilled abacus masters often calculated faster than early mechanical calculators. The abacus was more than a counting tool. It introduced a revolutionary concept, representing numbers physically in structured positions. Each bead carried value depending on where it was placed, a powerful idea that echoes through modern computing. In many ways, the abacus became humanity's first portable calculator and one of the earliest forms of human-computer interaction. Even today, the logic behind digital memory and positional value systems can be traced back to these moving beads. The road to the computer had truly begun. Imagine trying to build modern mathematics without zero. No calculators, no algebra, no computers, no binary code. For ancient civilizations, counting was possible, but advanced calculation was painfully difficult. Systems like Roman numerals had no true placeholder, making large arithmetic extremely complicated. Without zero, numbers could not properly represent absence or empty positions. The difference between 10, 100, and 1,000 becomes impossible without placeholders. Humanity had numbers, but it still lacked the concept that would unlock infinite mathematical possibility. Centuries before modern science, an Indian mathematician and astronomer began transforming humanity's understanding of numbers and the cosmos. His name was Aryabhata. Around 499 CE, he wrote the Aryabhatiya, one of the most influential scientific texts of the ancient world. Aryabhata calculated planetary movements, estimated the value of pi with astonishing accuracy, and proposed that Earth rotates on its axis. His mathematical innovations laid the foundation for later scholars who would revolutionize the concept of zero and arithmetic itself. Building upon centuries of Indian mathematical advancement, another brilliant scholar changed mathematics forever. In 628 CE, Brahmagupta formally described zero not merely as a placeholder, but as a true mathematical number. Brahmagupta explained mathematical operations involving zero and negative numbers, creating rules that would eventually power algebra, science, engineering, and modern computing. Without zero, computers could never exist. Through trade routes and scholarship, Indian mathematics spread westward into the Islamic world, where scholars preserved, expanded, and translated these revolutionary ideas. Centuries later, these numerals entered Europe and became known as Arabic numerals because Europeans encountered them through Arabic scholars. Yet their true origin was India. Today, every computer on Earth still depends on this ancient invention: zero. Every computer program, every app, every search engine, and every artificial intelligence system follows one fundamental idea: the algorithm. An algorithm is simply a step-by-step method for solving a problem. Even ancient humans unknowingly used algorithms, following repeated instructions for counting, building, farming, or navigation. Long before computers existed, humanity had already invented computational thinking. In the 9th century, a Persian mathematician working in Baghdad changed the future of mathematics forever. His name was Muhammad ibn Musa al-Khwarizmi. His works on arithmetic and systematic problem-solving became so influential that his name eventually evolved into the word algorithm. He also helped spread Indian numerals and algebra across the Islamic world and Europe. Centuries before electronic machines, algorithms already powered civilization. Merchants used procedures for accounting. Astronomers followed step-by-step calculations to predict eclipses. Engineers used mathematical instructions to construct monuments and irrigation systems. Computers did not invent algorithms. They simply automated them at unimaginable speed. In 17th century France, a teenage genius became frustrated watching his father struggle with endless tax calculations. His father worked as a tax commissioner, spending hours adding massive columns of numbers by hand. Determined to help him, a young Blaise Pascal began designing a machine that could calculate automatically. He was only 19 years old. After years of experimentation, Pascal created the Pascaline, one of the world's first mechanical calculators. Using a complex system of interlocking brass gears and rotating wheels, the machine could automatically perform addition and subtraction. Turning one wheel would mechanically carry numbers forward, just like modern digital arithmetic logic. For the first time in history, a machine could reduce human mental labor. The Pascaline was expensive and difficult to manufacture, so only a small number were built. But its true importance was revolutionary. It proved that machines could process information automatically. Pascal's invention inspired future generations of inventors who would create increasingly advanced calculating machines. Centuries later, every calculator, computer, and smartphone would trace part of its ancestry back to those spinning brass gears. As Europe entered the scientific revolution, another brilliant mind pushed mechanical calculation even further. Gottfried Wilhelm Leibniz believed machines should do more than simple arithmetic. He imagined a future where logical reasoning itself could be automated. While still a young scholar, Leibniz became fascinated by the idea that human thought might someday be translated into mechanical processes. In the 1670s, Leibniz designed a powerful calculating machine called the stepped reckoner. Unlike Pascal's machine, it could perform multiplication and division automatically using an ingenious mechanism known today as the Leibniz wheel. But Leibniz's greatest insight was even more extraordinary. He realized that all numbers could be represented using only two symbols, 1 and 0, binary. At the time, this idea seemed philosophical and abstract, but centuries later, every computer on Earth would run entirely on this exact principle. In many ways, Leibniz saw the digital future long before electricity itself. In the early 19th century, mathematics powered navigation, engineering, astronomy, and finance. But calculations were still done by humans, slowly, painfully, and often with dangerous errors. Frustrated by these mistakes, Charles Babbage envisioned something revolutionary, a machine that could calculate automatically with perfect precision. Long before electronic computers existed, Babbage imagined the future. Babbage's first great invention was the difference engine, a massive mechanical calculator designed to compute mathematical tables automatically. Using thousands of precision-engineered brass gears, the machine could solve complex polynomial equations without human error. Governments hoped it would revolutionize navigation, engineering, and astronomy. But Babbage soon imagined something far greater. The analytical engine was not just a calculator. It was the blueprint for the modern computer. It included a processing unit, memory storage, input through punch cards, and even conditional operations. Astonishingly, nearly every major component of today's computers already existed inside Babbage's design, entirely mechanical. Yet, despite his genius, Babbage faced endless problems. Lack of funding, engineering limitations, political conflicts, and public skepticism. His machines were too advanced for the manufacturing technology of his era. The world would wait nearly a century before realizing how far ahead of time he truly was. Charles Babbage never saw the computer age, but he helped invent it. In Victorian England, society rarely encouraged women to pursue mathematics or science. Yet one extraordinary young woman would become one of the most visionary minds in computing history. Ada Lovelace was the daughter of the famous poet Lord Byron, but her mother pushed her toward mathematics and logic instead of literature. Ada grew fascinated by machines, patterns, and the hidden structure behind numbers. When Ada Lovelace encountered Charles Babbage's analytical engine, she immediately understood something others did not. The machine was not merely a calculator. It could follow instructions. While translating a scientific paper about the engine, Ada added her own detailed notes, including a step-by-step method for calculating Bernoulli numbers. Historians now recognize this as the world's first computer program. But Ada Lovelace's greatest achievement was not just writing the first program. It was her imagination. She realized that computers could someday manipulate symbols beyond numbers, including music, language, and art. More than a century before modern computers existed, Ada envisioned machines creating and processing information itself. In many ways, she predicted the digital world, and even artificial intelligence. Modern computers perform billions of calculations every second, yet deep inside, they understand only two states, on and off. This simple two-symbol system is called binary. Instead of using 10 digits like humans, binary uses only 0 and 1. Why? Because electronic circuits can easily represent two stable conditions, electricity flowing or not flowing. From this simple idea, the entire digital world emerged. At first glance, binary looks strange, but its logic is beautifully simple. In decimal counting, each position represents powers of 10. In binary, each position represents powers of 2. So the binary number 101 equals 5 in decimal, 14, 02s, and 11. Using only zeros and ones, computers can represent every number, image, sound, and video ever created. In the 19th century, an English mathematician named George Boole made a discovery that would become the foundation of modern computing. Boole realized that logical reasoning could be expressed mathematically using simple true and false relationships. His system, now called Boolean logic, allowed machines to process decisions using operations like and, or, and not. Computers do not think like humans. They think through logic. Every 0 or 1 inside a computer is called a bit, short for binary digit. 8 bits together form a byte. From these tiny building blocks, computers construct everything: text, music, photographs, movies, video games, and artificial intelligence. Every digital experience you have ever seen is ultimately built from enormous oceans of microscopic electrical switches flipping between 0 and 1. In the early 20th century, mathematics faced a profound question. Could every logical problem be solved mechanically? One young British mathematician dared to answer it. Alan Turing was quiet, brilliant, and deeply unconventional. Long before modern computers existed, Turing began imagining machines that could process instructions automatically, not unlike the computers we use today. In 1936, Turing described a hypothetical device now known as the Turing machine. It was astonishingly simple, a machine that reads symbols on an infinite tape and follows instructions step by step. Though purely theoretical, the Turing machine introduced the central idea behind all modern computing, a machine that can execute programmable instructions. But Turing's greatest breakthrough came next. He realized that one machine could potentially simulate any other machine simply by changing the instructions. This idea became universal computation, the foundation of modern programmable computers. Every smartphone, laptop, and supercomputer today follows this exact principle. When World War II erupted, Britain recruited Turing to work at a secret intelligence center called Bletchley Park. There, thousands of cryptographers raced against time to break Nazi Germany's encrypted communications. German military messages were encrypted using the Enigma machine, a device considered nearly impossible to crack. Turing helped design electromechanical machines called bombs that rapidly tested possible code settings. The breakthrough helped Allied forces intercept critical enemy communications and may have shortened the war by years. After the war, Turing turned his attention toward a radical idea. Could machines think? In 1950, he proposed the famous Turing test, a thought experiment asking whether a machine could imitate human conversation convincingly enough to fool a person. This question became one of the foundations of artificial intelligence. Despite helping save millions of lives during the war, Turing faced persecution from his own government because of his homosexuality, which was criminalized in Britain at the time. One of history's greatest scientific minds was punished by the society he helped protect. Alan Turing died in 1954 at just 41 years old. Yet his ideas transformed the world. Modern computer science, software, cryptography, artificial intelligence, and programmable machines all carry his influence. Today, billions of computers operate according to principles Turing imagined decades before the digital age truly began. The modern world runs on ideas born in his mind. Thanks a lot for watching. If you're liking the videos, please do like, share, and subscribe.